Okay, so what we are discussing is spectral reflectance properties of different materials. Last class we have seen reflectance of water and soil. So some of the important factors which affects I have told you. And today we will see about say these are some examples which I think I showed you in the last class sometime. How sediments will change the reflectance in a true color composite image, and similarly how phytoplankton like the algal bloom, how they will be visible. Okay, so that is one thing. So with that background, we will move ahead. We'll move ahead seeing the spectral reference properties of snow, and with that we will finish the spectral reference curves part. Then we will move on to spectral indices, okay, like different indices like NDVI, NDW and all, then we will see that today. So regarding snow, snow is nothing but a collection of ice grain, air and some sort of impurities, maybe some water. Okay, it's just ice, air, water mixed together. Sometimes it may be dry, sometimes it may be like partially melted. So different states of snow will be there. And snow can exhibit quite a lot of variation in terms of its grain size, density, depth, water content, etc., etc. Very suddenly it can change, and snow at one place can be completely different from snow at other place. One can be like a larger grain size, one can be smaller grain size. Some sort of impurities may be there in one. Depth can be very thick in one place, depth can be shallow in another place. So snow exhibits quite a lot of variation. And also snow has the highest reflectance, especially in the visible bands, when compared with any other material in Earth. It will always appear like extremely bright when you see in any of the visible band, be it red, green, blue. That's why it appears pure white. Pure snow appears white because it has high reflectance in all colors, red, green and blue. And since high reflectance is in all colors mixed together, we see it as white in color. That's all. And then, but snow can quickly change its reflectance because of change in characteristics. Like as I said, metamorphism. Metamorphism means its physical form can change, its grain size can change. It can melt, forming liquid water. Some dust can come and settle over a layer of snow. All these things can quickly change the reflectance of snow. And we are going to see like some important reflectance properties about snow, important factors which affects the reflectance of snow. So mainly the properties of snow depends on the properties and geometry of ice grains that is present. Okay, basically what type of ice grain is present and what geometry it is oriented, along with liquid water present, any impurities present, all these things will together determine the reflectance from snow. The major factors which affect snow reflectance are first thing, grain size. Maybe we leave this because we all know that with wavelength reflectance changes. So this is kind of like a redundant point. So you can leave it. But with respect to snow, grain size and age. Grain size means what is the size of each and every snow particle. That is important. How much water content is there, whether it is a dry snow or it has melted liquid water present within it. The solar zenith angle, thickness or depth of snow, what we call snowpack thickness, and presence of any dust or contaminants. So these are some important factors which affects the reflectance from snow, and we will see one by one what it will happen. First thing, how snow reflectance will look. That's what we are going to see now. That is, what is the general reflectance property of snow? As I said, in visible band, that is up to this 0.7 micrometers, reflectance is quite high. You can see it's almost above 90% in all the bands, red, green and blue bands. Then the reflectance slowly decreases from NAR band, okay, and it decreases and finally comes to very low value after this 1.4 micrometers. So it is kind of like almost like a continuous decrease, and after it it's very low after 1.4 micrometer. This is how the pattern looks. So this is can be remembered as opposite to soil. Like when you studied soil, soil had like more or less increase in all the wavelengths. For a snow, it will start with very high reflectance and it will slowly decrease. That's all. And the decrease will be seen up to this 1.4, after which it is low. So this is with respect to the variation in wavelength. Okay. In addition to that, we will also see one more property, that is how the grain size affects snow reflectance. Say this blue line is for smaller grain size or fine snow. This orange color is for larger grain size or coarse snow. So from this, what you can understand is larger the size of snow, lower will be the reflectance. Larger grain size, lower reflectance. So this is one property which you should remember, but more or less the trend remain the same. Okay, but one thing you have to remember is for fine snow, what you can see here is there is absorption in the water absorption band around this 1.4, 1.9 micrometers, but after which there is some increase. Okay. For fine grain snow, after this 1.4 micrometers, there is some increase and decrease up to this 1.9. And similarly, after 1.9, there is some increase and decrease after 2.4. Like there is another band 2.7 micrometers, which is water absorption band. So these bands are seen, but in between there are like some peaks. Whereas for coarse grain snow, such peaks are missing actually. So you can see here, the peaks are not actually there. Okay. So this is what like is the general trend of reflectance from snow. So the general property is the reflectance is much higher in visible bands and reduces significantly in the IR bands. It slowly decreases in NIR and then it becomes very low in SWIR bands beyond 1.4 micrometers. So this is again the similar chart, but it shows for multiple grain size what will be the snow reflectance. So as you can see here, we have plotted different grain size starting from 50 micrometer radius, very small, to 1000 micrometers radius. 1000 micrometer radius means like 1 millimeter. So even though it's very small particle, but we are starting from extremely tiny snow particle to up to 1 millimeter snow particle. So as you can see here, as the size increases, as the grain size increases, the reflectance decreases in all the bands. No questions asked. In all the bands, the reflectance will go down with increasing grain size. And also what you can see here is after this band around this after this 1.4, there is like a dip here. Similarly, after 1.9, there is a dip. It's not exactly at 1.4 and 1.9, slightly after it. So remember, water absorption bands are at 1.4 at 1.9, but for snow, it occurs slightly after that part, after 1.4 and after 1.9. After which the increase or the peak that is attained is much larger for fine grain snow. So this also you have to remember. After these absorption bands, the peak that comes is much larger for fine grained snow when compared with coarse grained snow. For snow with larger grain size, the increase is very small, as you can see here. Okay. So this is another point you have to remember. And third point is just compare the difference between each line in visible band and NIR band and SWIR band. So the difference is very small in visible bands and difference is quite high in NIR and SWIR bands. That means the amount of difference or the change in reflectance in snow with varying grain size is very small in visible bands, whereas it is quite high in NIR and SWIR bands. So that is given here in this chart on the right side. This is a relationship between snow grain size and the reflectance, okay, at different wavelengths. You can see here, you are starting with blue band here, and this is NIR and this is SWIR. So as you can see, as the wavelength increases, Even a small change in grain size is causing a large change in reflectance. So here, for lower wavelength, the change is very small. That's why you are getting like a linear line with smaller slope. Very small slope indicating the change is very small with increasing grain size. But when you see here, the curve, when you increase the wavelength to 0.8, the slope is more now. That means more higher change will be seen. After which slowly the curve changes to kind of like a polynomial curve or an exponential curve, indicating that with increasing wavelength, the effect of increasing grain size will become more prominent. That is, with larger wavelength, more difference will be observed when the grain size changes. So this you have to remember. You cannot just assume that, okay, in all the wavelengths, the reflectance will have same difference. The difference will be very small in visible bands, slightly larger in NIR and much larger in SWIR. So this is the property you have to remember clearly. Okay. Any questions in this? Like here we are seeing how reflectance will change with respect to wavelength and also with respect to grain size. Any questions?
No, sir.
Okay. Okay, next thing is, next factor that we are going to see is age of snow. Older snow generally tends to have larger grain size. Larger the age, larger the grain size. This is like a general trend seen in snow. Okay, snow tends to compact or join with each other and form larger particles. When larger particles are formed, then reflectance decreases. That's all. That's all that we know. So this is again like fresh snow and a 20-day-old snow. You can see the density is different. Older snow is more dense and also it will have larger grain size, and typically it will have lesser reflectance than fresh snow. So if you have like side by side young snow and the slightly old snow, you can identify the old snow by decrease in reflectance. Okay. Next thing, presence of water within snow. When water is present within snow, the reflectance decreases. More almost in all wavelengths, the reflectance will go down. Okay. But here you may have to remember one thing, that normally what we will think when water is present, water is a very good absorber of energy, especially after NIR wavelength. So we may think, okay, since water is present, it is absorbing a lot. However, the reality is water is not acting as an absorber there. But when snow and water gets mixed together, snow tends to form larger grain clusters. That is, individual grains will come and stick with each other if liquid water is present. That means it will act as one large grain rather than many small grains. It will cluster together or combine to form a larger grain. That is why the reflectance is going down. So it is not because of absorption capacity of water, but it is the property of water which sticks snow particles with each other, thereby forming larger grain size. Okay. So here in this particular chart, three different curves are drawn. One is for a proper old snow, that is curve A. Curve B is for wet snow which has melted water within it, and curve C is for the same snow after melting. Sorry, after freezing again. So snow can melt as well as freeze, right? After freezing. So what you can see here is original snow without the effect of melting and freezing and everything has higher reflectance. And then when snow melts, its reflectance goes down. Curve B is much lower. After that, the snow has frozen. So the liquid water has frozen, but still the grains will remain at a larger size. Once it sticks together, it will stick and form like a larger grain size. It is not going to change. That's what we call like one of the metamorphism of snow. It is like change in physical property. It has melted, and due to the melting, all the particles came together and stick as one single grain. Even if it freezes again, still the grain size will be much larger than original condition. That is why the reflectance has not increased. See, the curve C and curve B is very close. They are not different. That means if a snow is original in its original state, its reflectance will be different. If it has melted, the reflectance will come down. If it refreezes again, the reflectance will not go back to original state, but it will be affected because of this melting and refreezing. So this is also maybe a cause. So snow may be completely frozen, but it might have melted before, which might have changed its grain size and hence reducing the reflectance. And then the next factor we are going to see is solar zenith angle. This we have not seen for any other features, like how reflectance will change for different solar zenith angle. So zenith angle means this one, the angle with respect to the vertical, in which angle sun is present. Okay, so this is the zenith. This is called zenith angle. So what? But for snow, actually, we are seeing, because snow will have drastic change in reflectance and across all wavelengths. For other features, say vegetation and all, this has to be like, it's quite complex to study also. We need to completely know how the object also will behave. But for snow, we are studying this, which is different from other features. So the reflectance generally increases with zenith angle. That is, as the sun moves towards the horizon, we will have higher reflectance. So you can see zenith angle 0. That means exactly at nadir. Slowly it goes towards horizon. Then here this is like zenith angle 80, very close to horizon, almost like setting sun. So you can see the reflectance of snow is higher. It increases and increases with increasing solar zenith angle. And here also the difference or the increase is much lower in visible band, whereas it is much higher in SWR band. So this also you have to remember. Okay, so it is very similar to how grain size will affect, but in the opposite direction. In grain size, larger the grain size, smaller will be the reflectance. In case of solar zenith angle, larger the zenith angle, larger will be the reflectance. And the difference, like the increase in reflectance here, is much smaller in visible wavelength, whereas the increase in reflectance is much larger in IR wavelengths, infrared wavelengths. But increasing zenith angle will increase the reflectance. That's a general property you have to know. And the final property that we are going to see is presence of dust. And this is also very important actually with respect to climate influence. That's know how it influences climate. This is fairly important property. What will happen is, even like a tiny amount of dust, when it get deposited over snow, it is going to change the reflectance drastically. So this is like the same area, the two figures. But this is just after winter, that is spring season. Okay, just in the beginning of spring season. This is just in the beginning of summer, after spring, before summer. So what would have happened? Snow would have melted. In spring season, snow will melt, vegetation will grow, all will happen, but also dust would have settled down. So these portions where dust have settled, you can see how much change in reflectance is seen in snow. Snow will become, what to say, the reflectance will change drastically with the presence of dust. Actually, this is what, like, even in climate, for climate studies, people are like, will be talking about how much dust is depositing over snow. Like, many people, you might have heard somewhere that more and more burning or more and more dust created in other parts of the globe will trigger snow melt. Because what will happen, as dust settles over snow, its reflectance will go down. If reflectance goes down, naturally absorption will increase. So more the absorption of solar radiation, snow will get heated up and it will melt fast. So dust snow will accelerate melting actually. When melting accelerates, water will form. Water will change the grain size, which will further decrease the reflectance. So it will start a chain reaction kind of thing. So the presence of dust over snow is extremely critical because it triggers all the other associated activities like melting, removal of snow and everything, which is important even for like a global climate. So this is one important property which normally people look after, whether the snow is fresh, whether the snow is clear or it is dusted, all these things. So this actually brings us to the end of spectral reflectance part. Final one thing what we are going to see is how to distinguish between snow and cloud. Normally in visible bands, both will appear very bright white in color. And especially if you observe any images over snow covered regions, and if some clouds are present, you will not be able to distinguish whether it is cloud or snow. Both will be white and both will match with each other. But to identify whether it is a cloud or snow, it is always good to observe in SWIR bands. After this 1.4 micrometers, snow's reflection come down drastically, but cloud will still have high reflectance. So if at all you want to distinguish whether there is snow or cloud, you have to observe at SWIR wavelength. So this wavelength is actually used to distinguish between snow and cloud in many of the operational snow products. Maybe we will see later. Okay, so this point you have to remember which wavelength you have to use to see or distinguish between snow and cloud. It is SWIR. Any wavelength greater than this 1.4 micrometers is useful. Okay. So with this, we come to the end of spectral reflectance curves. We have seen spectral reflectance of vegetation, water, soil, and snow. So here, what I expect you to remember is what is the general reflectance pattern of each feature at different wavelength. What are the important factors that will affect the reflectance, and how the reflectance will change with different factors. And the numbers, when you draw a graph, if I ask you to draw a graph in exams, you should draw properly with the X and Y axis. What is the wavelength here correctly? What is the reflectance here correctly, as given in the slides. The slides are posted in Moodle. You can study based on the slides, no problem. But I want the numbers because I have seen several students just drawing the curve like this without marking anything here. Is it 5% or 50%? What number I should fix there? That you should write always, and also at which wavelength it happens. That also you should mention. So drawing the curve is not straightforward. You cannot just draw a curve and leave it as it is. I expect you all to properly study the curves carefully, note the numbers at X and Y axis, and if you are asked to draw any one of them, I want it to be perfectly reproduced. Then only you will remember, okay, what is the influence. If you just miss the numbers, it is of no use in studying this. But this is theory part. It is almost like you have to study and remember. There is no escape because this is not like an equation with physics behind. It's like theory, what happens, which we cannot explain it further. Okay. So with this, we move to the next topic or the final topic before mid-semester. That is vegetation spectral indices, or not only vegetation, in general spectral indices. What are spectral indices? Till now, we have seen about reflectance in individual bands. What will change? What is like the key factor which affects the reflectance and all. But for all applications or for all purposes, it will not be feasible to look at the reflectance continuously. Like we may not get the complete reflectance curve always, but still we may have to do some work based on the data. There comes these spectral indices. So the spectral indices are nothing but a single number which is formed by combining reflectances in two or more than two bands in some fashion. So you have like a multispectral data, say red, green, blue, NIR, SWIR, all wavelengths images are there. Rather than just seeing them as individual images, you combine them using some mathematical formula and create a new layer. and that layer will give you somewhat more information or clear information about the feature that you are studying about. So that is the spectral index, and there are like more than 100 spectral indices available. It is not one or two, more than 100, and we cannot study everything. We will limit ourselves to some of the most commonly used indices, what is its use and for why it is created. That's what we are going to study. Okay, so now we know what a spectral index is. It's a number formed by combining two or more things. Why we should combine this? What is the need for creating such spectral indices, and that to hundreds? The first thing is the important property or the important reason for which such spectral indices are created is to improve sensitivity to some biophysical properties. That is, here I have talked with respect to vegetation, but it is true for all the sense. In order to highlight some features on the ground, we use these spectral indices. Okay, that is, let us say you have like one small area. You need to identify all the open water bodies present within the area. Okay, so your ultimate goal is creating like a binary map. Okay, this is a water body, this is not a water body. So to highlight this, people would have devised an index by combining reflectances in some bands. Similarly for snow, there is like a snow index, and similarly for vegetation, there is a vegetation index. So the purpose of creating the spectral indexes is to highlight certain properties or certain features. Okay, that is the first thing. Second thing is, when we have studied about the reflectance from different objects, I have told you that the reflectance is affected by several factors, like the sun solar geometry, the satellite viewing geometry, the BRDF, basically the BRDF of the object, how the reflectance will change with change in solar and satellite viewing geometry. And similarly, the topography, whether the surface is flat or it is on a slope, that will change reflectance. Atmospheric effect will be there. Soil effect will be there. Like if you see vegetation, you may be seeing some sort of soil. So there will be many other factors which influences the reflectance. So these sort of indices tend to reduce some of these factors. Okay. As a single example, like yesterday in lab, you came across this topography correction, right? Maybe when you do that exercise by your own hand, you may able to see that over slopes, the reflectance change is quite high. Okay, for the same object may be present on a flat surface and a sloping surface. Over slope, the reflectance may be totally different. It can happen because in which direction sun is, in which direction the satellite is, everything is going to matter. Let us say sun is here, satellite is here. There are like vegetation standing here on this side. So this part is on a shadow because sun is lighting up this side, but this part is shadow. So the image over this region will be darker. The reflectance will be naturally lower in all the bands. Okay. So the reflectance can change due to anything. So people decided to reduce this effect to some extent, especially this sort of shadowing effect and topographic effect. So without doing topography correction, they wanted to develop some simple methods, especially for vegetation monitoring. They came up with what is called spectral ratio. So spectral ratio is nothing but reflectance in any one band divided by reflectance in any other band. Okay. This sort of ratio they first found out, especially for vegetation. They came up with reflectance in NIR divided by reflectance in red. This ratio people found out, even if vegetation is present within shadow or snow, it increases, or we are able to clearly see the vegetation. It reduces the effect of topography. So for such effects, people first came up with this spectral ratio. So it is like it reduced the topographic effect to some extent, and it made clearly visible. The vegetation became clearly visible. So people were using this sort of ratio for a long time, especially this NIR to red ratio. This is called ratio index. Its name itself was ratio index. So this was one of the very first created spectral index. Okay. But the problem here is, since it is a ratio, it is unbounded. Unbounded in the sense, the range of this particular ratio will vary from 0 to infinity. If red is very close to 0, the ratio will be very high. And similarly, if NIR is very close to 0, it will become 0. Okay, so the value ranged from 0 to infinity without any number. So people were not able to really understand. Let us say in one image or in today you get an image. After 1 week you get another image. This is today. This is after 1 week. Here you see one number. Let us say the ratio is 1.5. After that, the number suddenly jumps to 7.89 because it can go up. It's unbounded. What is the real meaning of this? Is 1.5 or is 7.89 much higher than 1.5? What is the real meaning? So that sort of physical reasoning was not possible with this unbounded range. When a number changes from 0 to infinity, you cannot say what causes that. It is basically because due to very low denominator. That's it. But no physical reason can be given. This actually prompted people to devise better indices with much higher with much higher properties. Okay, with much better properties. So with this background, now we will go and see some of the few commonly used spectral indices. The first one and most widely used one is NDVI, Normalized Difference Vegetation Index. So this index is this index was produced after the ratio index. Say ratio index was NIR by red reflectance. This is produced in a normalized pattern. Normalized in the sense the formula NIR minus red by NIR plus red. So this ratio index was changed something to like this. The main advantage of creating an index is it helped to clearly highlight the presence of vegetation. On the other hand, because you are dividing this with like a the numerator will be always like the absolute value of numerator will be always less than denominator. That is why this is bounded. Bounded means the value will always range from plus or minus 1. Since the value is always ranging from plus or minus 1, you can compare. Okay, today it is 0.6. After 1 week it is 0.7. That means there is increase in vegetation. So that sort of comparison was actually possible because of this bounded nature. It is not now unbounded anymore. And this particular vegetation index, NDVI, has been shown to be highly correlated with chlorophyll content. Okay, so higher the chlorophyll content, higher the vegetation activity, like healthier the vegetation, NDVI will be much higher. And normally when you take a pixel, if the value of NDVI is negative, it means it is most likely water or cloud or such features like non-land. It's not land part. Okay. NDVI between 0 to 0.2 or 0.25 may be treated as soil or cloud contaminated pixels. Like it's like 1 pixel which is partially covered with cloud, or it is like a pixel with bare soil without any vegetation. If NDVI is more than 0.2 or 0.25 and up to say 0.6, it is kind of like a mixed pixel. Mixed pixel in the sense mix of both soil and vegetation. And finally, if NDVI is greater than 0.6, most likely the pixel is fully covered with vegetation. So this sort of numbers we can actually attach to NDVI. Just by seeing that number of NDVI, you may get to know how much vegetation may be present within a pixel. So that's sort of some minimum information or minimum knowledge. It will be very easy to obtain by looking at this NDVI image. Okay. So now any one of you should tell. I said this is related to chlorophyll content. Okay. Why do you think NDVI is more related to chlorophyll content? What makes NDVI an indicator of chlorophyll content? Just look at the NDVI formula and anyone say what is the main reason behind it.
Sir, NIR band?
No. Actually, it is the red band. The presence of red band is what to say, will actually help us to identify this identify or help us understand the chlorophyll content. Okay, because you just recall the spectral reference curve of vegetation, how it will change. If something happens to chlorophyll, immediately the first difference that will come in visible band, like the red reflectance will increase. I told you about what is called a blue shift of the red edge. I told you about this, right? If let us say some vegetation stress is happening, what will happen immediately? The red edge quantity, that portion will come down, will decrease. Red reflectance will increase. The red edge will become smaller and the wavelength and at which red edge occurs will go shorter. So any change in chlorophyll will first affect the red reflectance rather than affecting NIR first. So any change in chlorophyll will immediately signal here. This reflectance will increase. Thereby the numerator will come down. NDVI will definitely decrease fast. So the presence of red and NIR, because NIR will not change that easily. NIR will take quite a long time to change. That also we have seen. Only when a leaf is like totally destroyed, NIR comes into picture. But this combination, but what here we are using is NIR always has high reflectance most of the time, but this red reflectance will be low if vegetation is healthy and it will increase if vegetation is undergoing any sort of stress. And hence this difference will decrease in case of any stress. We are taking that property to our advantage. We are here calculating. Actually, we are kind of like working with the red edge. How far is the difference between NIR and red reflectance? This difference will be smaller and smaller if vegetation is undergoing stress. And if vegetation is growing, let us say from bare soil to fully healthy vegetation part, if it is growing, this difference will become larger and larger. Okay, so that factor we are taking to our advantage and using it to calculate NDVI. Okay, so this is you may have to like keep this in mind, all these points in mind. So watch the video again, it will help you. Okay. Now we move to the second index, normalized difference water index, or also called as normalized difference moisture index. Two names are there. Originally, when the index was proposed, it was called NDWI, normalized difference water index. But later, due to some confusions, which I will tell in the next slide, some people also call it as NDMI, normalized difference moisture index. Okay. So this is very similar to formation of NDVI, but instead of red band, here we are using SWR band. Okay, this should be NIR, sorry. So SWR bands mean any band greater than 1.5 micrometers. Typically 1.5 to 1.7 micrometers is what we will use for this particular index. So the main purpose of creating this band is to observe vegetation liquid water content. So this also we have studied. I have clearly explained that whenever the amount of water present within a leaf changes, the first change in reflectance will happen in SWR band. Decrease in liquid water content will increase the reflectance in SWR band that I have told you several times. That property we are using here. Let us say we need to monitor if vegetation is healthy or it is undergoing any stress. If we are using NDVI, what will happen is for the chlorophyll to be affected, it may take some 3 to 4 days or sometimes even 1 week. Say the stress has to be there for up to say 4 to 5 days for chlorophyll to decrease and then NDVI to decrease. But a farmer cannot afford it. If there is like a decrease in water content, immediately the farmer should irrigate to save the crop. So immediately this water stress should be identified. So which band will give that signal? SWR band will give the signal, an immediate signal about any water stress. That's why people have used this SWR band here. Here also, NAR reflectance will be fairly high always. Okay. Only if the leaf is totally dead, NAR reflectance will come down, else it will be fairly high. But for a very healthy vegetation with very good water content, SWR reflectance will be low. If vegetation water content decreases, SWR content will increase. So that means for a healthy vegetation with very good water content, what will happen is rho NAR will be high, rho SWIR will be low. That means NDWI will be high. Typically greater than 0.2 or 0.3, mostly in the positive side. For drier vegetation, say the vegetation is totally under water stress or it is bare soil completely, this will become very close to 0 or negative. Okay. So that will be the numbers you can see. Actually, this you can also compute using Google Earth Engine and just see how the values happen. Actually, you haven't done this exercise in lab. We have an exercise to compute spectral indices using different things. Okay. So this is about NDWI, which is related to vegetation water content. Okay, so this only you have to change. This is not SWR, this is NAR. Even the slide which I posted in Moodle, this mistake will be there. Please correct it. Always the numerator and denominator will be similar. If it is NAR minus SWR, the denominator will be NAR plus SWR. Okay, that you keep in mind. Okay, so here I have shown that this index was created in the year 1996. In the same year 96, another scientist called McPheeter created another index and he also named it as NDWI. But the band combination is different. He came up with a new definition of green minus NAR by green plus NAR. He developed this index to identify open water bodies. Okay, so normally again, you just recall the reflectance curve of vegetation. Sorry, water. Water will have slightly higher reflectance in blue and green wavelength. Reflectance will drop in red and it will become 0 in NAR. That property is taking. So combining green and NAR, we will be able to see if NDWI is positive. That means it may be like a water body. If it is negative, it is not a water body. So that sort of difference will be very clearly highlighted using this. This is for open water bodies. So this is what caused the confusion. Two indices with the same name, but with two different applications. One is for vegetation liquid water content. One is for mapping open water bodies, nothing to do with vegetation. So this difference still is present and many people confuse. In some paper, people have interchangeably used NDWI for open water body and all. Even like when I published a paper, the reviewer asked me, you are using NDWI, which is for open water bodies that is related to vegetation. Then I have to explain him, no, this NDWI has two definitions. I am using definition by Gao in 1996 that I use this definition and all. This confusion is present even today. So whenever you come across the term NDWI, please be careful in studying which bands are used. If it is NAR and SWR, it is for vegetation water content. If it is green and NAR, it is for mapping open water bodies. So this difference you should always know. Okay. And later in the year 2006, another scientist just modified this, renamed it as modified NDWI. Instead of like NIR, he said it's better to use SWR band. This is even more robust, even more it will highlight water bodies better. Okay. So this also you can use. You can also like try this and plot seeing water bodies. So fine. So we have like come across few indices. Now we will slightly spend some more time on the vegetation index. Okay, so vegetation index is slightly more important, at least because of its wide usage. So now we will spend somewhat more time. We will talk about NDVI first. I said NDVI is related to chlorophyll content in the leaf. If the vegetation is healthy, NDVI will be higher, else it is lower. But is it the only factor? Is it only the chlorophyll content which will change NDVI? No, definitely not. NDVI is affected by the atmospheric correction we do, the soil background effect, and also the actual amount of vegetation that is present on the ground. Three factors influences it. Okay. Atmospheric correction we all know. As we do any mistake in atmospheric correction, the final reflectance, what we get will change. It may change NDVI. That is straightforward, we can understand. You guys have done some atmospheric correction. Soil background effect. So what is soil background effect? Whether my remote sensing sensor is only seeing vegetation or it is seeing a mixture of vegetation and soil. That has to be studied. And also different crops or different plants will have different leaf structure. Maybe I will explain it with this slide. And third is the actual amount of vegetation that is present. Okay. So here in this slide, what is given is the change in reflectance for different crops. Okay, so each line is for one crop actually. I don't remember what crops they are now, but the crops are different with different leaf structures. We all know each crop has different leaf structure. Say for example, onion may look like this, very tiny straight leaves. Turmeric will have like an extremely broad leaf. Banana will have even broader leaf. So each crop has one type of leaf, and they may produce different reflectance. Okay. So for different crops, what will happen is the percentage of green cover is mapped. Percentage of green cover means within 1 pixel, what fraction of the pixel is covered with vegetation and what fraction is not vegetation, basically soil. So this can be from 0 to 100%. 0% green cover means completely bare soil. 100% vegetation means completely filled with vegetation, no bare soil. Everywhere it is vegetation. Okay. Under these conditions, people are plotting this reflectance in red band and reflectance in NIR band because these two are used in NDVI, right? So these two are plotted. Now you see here, the vegetation green cover is same. Like if you draw one straight line along the vertical, what you can see is the same amount of vegetation cover is present within that pixel. Effectively speaking, the reflectance should be more or less very close. Here also for NIR band, say the reflectance should be very close to each other. But here you can see for one crop, the vegetation is less than 10%. For another crop, the reflectance is almost 25%. Here also in NIR band, for same vegetation cover, in one band, the reflectance is around 20. In another band, in another crop, the reflectance is around 40. So something else is influencing because for same amount of vegetation cover, you expect very similar reflectance values. So what is influencing here is the amount of background soil that is seen. Like as I have said, the crops, different leaf structure, how the leaf are oriented, everything will change the way in which soil is seen. See, even like a single leaf of turmeric crop will obscure a very large soil part. Say this is the leaf, this may be the crop. Whereas, let us say we have some sort of like needle shaped leaves. It may be very high amount of leaf content, extremely thick, but the amount of ground cover produced by this needle-shaped leaf is very small. It may not shade the soil. We may be, when a remote sensing sensor sees this, for like a broad leaf, it may not see the soil at all. But for a needle-shaped leaf, it will always see a mix of leaf plus soil. Soil will always be visible. So this sort of mixture of soil and vegetation will change the reflectance. Okay, so that's what is seen here. Normally, only after the say 70% change or 80% change, that is almost 70 to 80% of my pixel is covered with vegetation, all the values converge together. For all the crops, the reflectance in red and NAR becomes very converged, else the difference is quite high. This is because of the change in soil background effect. Okay, so typically for soil, okay, now I pose you one question. In red band, which will have higher reflectance, vegetation or soil? Anyone?
Soil, sir.
Soil, exactly. So in red band, soil will have higher reflectance than vegetation. Similarly, in NAR band, vegetation will have higher reflectance than soil. This is the general trend, though it can change, but the general property is this. So if more amount of soil is seen, reflectance in red will be higher and reflectance in NAR will be lower. Okay, so that sort of things will come up. It will change the way in which we are seeing the things, or the NDVI will tend to change. Okay, so this is the effect of background soil. In order to account for this, Alfred Hute, he is a very big scientist who created, who's doing a lot of research in vegetation remote sensing. He came up with this soil adjusted vegetation index, SAVI. So the purpose of creation of SAVI is to decrease the background soil effect. So he came up with some derivation. The derivation I'm not going to explain here, but the final SAVI formula looks something like this. That is very similar to NDVI formula, but here we have one term 1 plus L and another term L in the denominator. This L is called the soil correction factor. Okay, so this L will vary based on whether there is high vegetation or low vegetation. 0.25, 5, 0.25, 0.5 and 1, 3 values are there. If we know how much vegetation is present within our pixel, we can choose L accordingly. Or to be on the safer side, people will always use an average value. L is equal to 0.5. Okay, some in-between value. So this index has been shown to decrease the effect of soil on remote sensing data. So the next factor which I said that will affect NDVI is atmosphere. So this you will actually experiment in your lab. So if you do, or if you compute NDVI with reflectance or top of the atmosphere reflectance, that is without correcting for atmospheric effects, you will get a different values. NDVI values tend to be lower, and if you correct for the effect of atmosphere, NDVI value tend to be higher. You can see from this histogram plot. Okay, so this is uncorrected NDVI, that is using TOA reflectance, and this is using surface reflectance after correcting for the effect of atmosphere. You can see here the peak is happening somewhere around 0.2. A lot of values are there in very low values, 0 to 0.1 and all. But here the peak has slightly shifted. Now the peak is around 0.3. There are some values close to 0.7. Here the peak itself stopped at around 0.6. Here the peak is 0.7. So essentially the histogram has shifted slightly towards right side, right? Because now the values of NDVI has increased. So what this means is atmospheric correction again will influence NDVI. So this is important. So that's why I'm repeatedly telling we have to use surface reflectance rather than DN or top of the atmosphere reflectance. Okay, because surface reflectance means we are correcting for the effect of atmosphere. DN, nothing would have been corrected. Solar effect, atmospheric effect, everything will be there. So DN is we cannot use practically. Top of the atmosphere reflectance, still atmospheric effect is there. Surface reflectance, there we would have removed the effect of sensor calibration, solar geometry variation, atmospheric effect and everything. So that's why it is always prescribed to use surface reflectance for all these vegetation indices computation and for most of your analysis too. So this is another example how NDVI changes with the atmospheric correction, but the point is already been told. So two properties we have seen, one is soil, one is atmosphere. The third property which will affect NDVI is, or the problem with NDVI is, what is called NDVI saturation. I'll select somewhat more time, it's already 12:30, but another 5-10 minutes I will take and I'll finish. What I said is NDVI saturation. What is meant by NDVI saturation? Let us say there is some pixel. For this pixel, you slowly increase the green cover, like percentage of green cover I have shown in an earlier slide, right? So as the green cover increases, NDVI tend to increase. After some increase in percentage of green cover, it will become flat. The increase will become flat actually. That is, you are increasing the amount of vegetation present within the pixel. Say this is 80% to 100%. You are increasing the amount of vegetation within the pixel, but still NDVI will not change. NDVI will become flat. It will reach some maximum value and it will become flat. It will not change. What this suggests is, at very high value of vegetation or for pixels that are highly vegetated, NDVI may not respond even if the vegetation is still growing. Say you are working over like a forest. Let us say it is like a very healthy thick forest. NDVI value, let us assume it is very close to 0.8. The forest may still be growing. It may be developing new leaves, new trees may grow. Still, the NDVI will be hovering around this 0.8, 0.75, 0.85 and all. It will not change much. This signals the saturation effect. After some range or after hitting an upper limit, NDVI value will not change even with growth of vegetation. That means it is the purpose for which NDVI is developed is getting affected. If there's more vegetation, NDVI should increase. That is we are missing. Okay. So three problems: atmosphere, soil, and this saturation effect is there. In order to overcome that, in 2000 or in year 99, when MODIS sensor was launched, the scientists working with MODIS science team came up with a new index called Enhanced Vegetation Index, EVI. EVI has very similar formula to NDVI. It still uses NIR and red bands. However, it uses a blue band primarily for atmospheric correction. So because blue band is highly affected by atmospheric scattering. So using that reflectance, we can calculate the path radiance and all. Okay, so that reflectance comes into picture. Very similar to SAVI, that soil correction factor L is used there. And to reduce the saturation effect, they are started to use this gain factor G. So it's a slightly modified form of NDVI by using this blue band, using the soil correction factor L and this gain factor G. By combining these, this EVI has to be shown to be better than NDVI. This is more resistant to atmospheric effect. Even if you miss correcting for the effect of atmosphere, still it worked better than NDVI. It is even when crop is growing or vegetation is growing, EVA still showed some signal, like it responded. Increasing crop, EVA still increased, thereby indicating it's not getting saturated. And by this factor of this L, we are also removing the effect of soil. So this EVA is now again being used as one of the most popular vegetation index. So people have commonly using both NDVI and EVA for various applications. But this EVA was developed very recently, 20 years before, whereas NDVI is there now for almost 45, 50 years. Okay. Fine. Yeah. And last but one slide. So now we have seen spectral indices for vegetation for open water bodies. Similarly, there are spectral indices for many other factors for identifying bare earth, for identifying built up surfaces. So there are plenty of indices. We cannot see everything. But just one more index related to the topic we are covering is snow index. So snow also, it uses green and SWR combined together. It's called normalized difference snow index. SWR, snow reflectance will be very low. In green band, it will be very high. Combining these two, people have designed a snow index for identifying snow covered regions. Okay. So this is actually, this index is used as one of the operational product in MODIS to identify snow cover region. So this will, if someone is interested in studying about glaciers, about snow and all, NDSI will come in handy. Okay, so with this, we end the spectral indices part 2. Okay, this part also we are completing. Why are we calling this as spectral indices? By the way, I am repeatedly mentioning this word spectral indices, spectral indices. Why am I calling it like this? Any reason you may think of?
Because we are talking like different bands.
Very good. We are talking about different bands. Whenever we talk about multiple bands at one time, we are studying about what is called change in spectral properties. Change in bands, we technically call it as spectral. That's why I'm using this term. Some book may not use this term. Okay, so that's why I asked this question in particular. A final word of caution. Whenever like we are working with this VAs, any VA, let us take NDVI. We normally tend to do a lot of mistakes unknowingly. Mistakes in the sense, we may combine data from two sensors together. Let us say you have one time series. Suddenly there is a gap in time series, and then you get a data from some other sensor, try to plug the time series. We cannot do that with VI. Okay, normally students tend to do, take two data sets, say one from Landsat, one from Sentinel, mix it together. That is not advisable. NDVI value tend to change with each and every sensor. Say for the same ground area, Landsat may have produced a lower NDVI and MODIS may produce a higher NDVI. Say for Landsat it may be 0.4, for MODIS it may be 0.5 or 0.6. It is happening. It is not theoretical, but in practice it is happening. This is because of the sensor effects. Okay, the spectral properties of sensor, how sensitive the sensor is, all these things plays a major role. Okay, so that is why you cannot mix data from two sensors together. Always we need to do some sort of like correction when we work with NDVI. Normally we cannot mix any sensor data for any reflectance, but for NDVI, sorry, for vegetation indices in particular, don't mix. And also, just don't trust the numbers of what is given by these indices. Let us say today you are seeing 0.5, after 1 week you are seeing 0.7. Vegetation might have grown in reality, but always have some ground truth values. Ground truth in the sense like what is really happening in the ground, please try to know it. Why? Because the indices, whatever be the index, it tends to change along with many factors like the BRDF of vegetation, the viewing angle, the amount of atmospheric correction we do. All these things will change the VI. And because of this, this particular vegetation indices, this EVI and NDVI together started a very big debate from 2010. It is still going on. Like there are like plenty of papers describing a very big debate. What the debate is, I think in the year 2005 or 2010, Amazon forest encountered a major drought. So normally what we expect, if it is a major drought, vegetation will die. So forest vegetation would have decreased. But one group of authors came up telling that Amazon became more greener after this drought. They analyzed this EVI and NDVI, and they said after the drought, NDVI values and EVI values are much higher than before. That's what they said, and what reason they gave is Amazon forest will have much larger trees. Just switch on my camera because it's just a story. Okay, so what they said is Amazon forest has very large deep trees, and with the deep trees it can extract water deep within the groundwater reserve. And what they said is during drought there was not much clouds, sunlight was much brighter, so sunshine was very high, trees were able to suck in water from underground groundwater reservoir, so no water stress, plants grow very healthy. That's what they said, and it became like a very big debate. Oh, okay, so drought has a positive effect in Amazon. But later, in the year from 2014 onwards, many people argued that the analysis that they showed is wrong. The increase in NDVI and EVI is not due to actual greening of forest, but it is due to the kind of atmospheric effect and the difference in solar satellite viewing geometry. Actually, this paper, if you see, you can just search for it in Google. You will get it. They would have clearly argued it is because of atmospheric effect and viewing angle. What they said is the same forest. If you are looking from one angle, say the trees are here, sun is here, satellite is also here. Because of directly sunlit shade, satellite will see this much brighter, leading to larger NDVI values. Same time, if the sun is here and the satellite is here, it will be satellite will be seeing a lot of shadowed part, thereby NDVI value tend to be slightly lower. So we said that NDVI will remove the shadow effect to some extent, it will not completely remove. That effect will always be there. So these sort of changes, along with poor atmospheric correction, they used older MODIS data. After the MODIS data were reprocessed with newer algorithms, NDVI and EVI values changed. So people said because of these, the negative effect came up. So it is not Amazon forest has greened. Actually, Amazon forest has lost vegetation, but it is because of the artifacts in this vegetation index, it has caused this problem. So this sort of debate is happening. It's a kind of a global debate, and papers are coming in much huge journals. Nature and all are like very big journals where people always believe, okay, whatever comes in Nature, it must be true. People believe it. But even in such papers, such journals, these sort of debates are happening. Okay, so that is why I'm telling, whenever you work with vegetation indices, most of the times it will be true, but always have a word of caution. Don't just believe, don't just go by numbers. Always better to have some sort of ground check. Okay. So with this, we stop. Any questions from your side? Actually, for midsum portion covered up to today will be there. And I think your exam is on Monday, 2:30 p.m. So initially it was said in morning 9 o'clock, but now the schedule has been changed. Last night HOD sent a revised thing. Monday it is at 2:30 to 4:30. Okay, so it's online. All our PG students, everything will be online. Same thing, you have to join that quiz link. What is there in our classroom? Join by 2:15. If you start by 2:45, join by 2:15. Sit with your face and hands completely visible. I need to see your top half. It should not be. Actually, you should not sit how I am sitting. I am sitting in a wrong position. During exams, please make sure your full hands are clearly visible. Your upper part of the body is visible, because it's for like supervision purposes. We need to follow certain guidelines. Okay. And you may have to, as usual, question paper will be uploaded in Moodle. Write, take a photographs, convert it into PDF, submit it. Okay. So Any questions, doubts? Nothing? One by one. Maybe Sachin.
Exam from where we get link, like it is in Moodle or like MS Team.
In MS Teams, you have to switch on, like we have to see your video, right? It should be like a proctored exam. So MS Teams, join the meeting.
Okay.
Like in MS Team, you have that in our classroom, we have a separate link, right? For quizzes, there is like a separate meeting link. Join that link. But your question paper will be uploaded in Moodle. So what you have to do is first join MS Teams, then in the browser open Moodle, download the question paper, start writing in a sheet of paper, scan it, again upload it in Moodle as a PDF. That's all. So till you write, you have to be within this meeting with your video on. That's all. Okay.
Like screen recording and nothing,
No, I don't insist on screen recording. I trust you people. I hope you will be like, what to say? You won't betray me. That's
honest,
the only thing.
Honest.
Okay. Honest. You will be honest. Yeah. So I believe you. I don't insist on screen recording, but
yes, sir.
Others will insist on screen recording. Professor E.P. Rahandal will definitely want you to upload. It's not that they don't believe you, but they are more strict in following the institute rules. Institute rule mandates screen recording, but I am little lenient on that side. So be honest, be trustworthy, write the exam. That's all. Okay.
Some numericals also you can expect now, sir, in exam, mid-sem.
Yes, yes. Actually, your quiz was entirely theory. Here there will be some numericals. Yes.
Yes, sir.
You can expect. Okay. But read theory also. Don't miss theory. Your seniors did the opposite. When I gave entire numerical, they never expected a theory. When I gave theory, they got shocked. Prepare for both.
But we are all more experienced with theory. Like quiz and all is like fully theory one.
Okay, for your case it reverse, but expect numericals. At
Yes,
least
sir.
one problem will be there.
Yes, sir.
Okay, fine. Okay, guys. So do well. Tomorrow is Ganesh Chaturthi. Maybe.
Sir.
Yeah.
Sir, if in between exam, sometimes like because of weak internet connectivity